Well, we have been talking about binomial models and geometric models. Can any of those models kind of represent a normal distribution, the normal model? Remember we talked about this months back, so I'll do a brief overview. Remember, normal model looks like so, where I have my mean right here, right dead in the center, and going from one standard deviation from the mean in both directions gives me 68% of my data. Going in 2 standard deviations is 95% of my data, and going 3 standard deviations from the mean is 99.7% of the data. So can any of our binomial or geometric kind of represent this kind of model? Well, there's a test, and that is the success-failure condition. A binomial model is approximately normal if we expect at least 10 successes and 10 failures. So the formula here is NP, is that greater than or equal to 10, and NQ, is that greater than or equal to 10. Where N is my number of trials, and P is my probability of success, and Q is my probability of failure. So NP greater than or equal to 10, or NQ, and NQ has to be greater than or equal to 10. Let's look at an example. A certain tennis player makes successful first serves 70% of the time. Assume that each serve is independent of the others. If she serves 80 times in a match, what is the mean and standard deviation of the number of good serves? B, verify that you can use a normal model to approximate the distribution of the normal of good serves, and use the 68, 95, 99.7 rule to describe the distribution. So the mean and standard deviation. If you can remember, to find the mean, it is N times P. So what is my N value for this problem? There you go, 80. What is my P value, my probability for success? 0.7. And what is my Q? 0.3. Do you see how they got 0.3 now?
Oh.
0.7 minus 1, the other percent is 0.3. So if I'm 70% failure, then I'm 30%, if I'm 70% success, I'm 30% failure. So to find my mean, it's N times P. So 80 times 0.7, which equals what? 56? Okay. So that is my mean. She'll make about 56 serves out of 80. And my standard deviation looks like this. It is the square root of NP times Q. So it equals the square root of 80 times 0.7 times 0.3. Somebody with the calculator, can they give me that? Let's see. Yeah, no. Let's say 4.01. 4.01. Yes, they're being used by PSAT right now. So there's my mean and standard deviation. Now B, can we verify that you can use the normal model? Well, we're going to use our success failure condition. So NP, is that greater than or equal to 10? Yes. Well, I've already done NP, and it's 56. Is 56 greater than or equal to 10? Yes. So that one's good. And what about my failures? That is NQ. So N times Q equals 80 times 0.3. So what is 80 times 0.3? What's that? 25? 4? 24. Is that greater than or equal to 10? Yep, so it's good. So I can actually use my normal model to approximate the distribution. And here's our normal model. Once again, one standard deviation is 68%, both left and right. So how can I do, what would be one standard deviation for 56? Go on to the right. You would take 56 and do what? Add 4, and go to the left, subtract 4, right? So I'll switch to the answer page here. So to find 68%, that is one standard deviation. So 56 plus 4 gives me 60, roughly. And 56 minus 4 gives me 51.9. To go from my 95% range, that is 2 standard deviations. So take my standard deviation, multiply by 2, and add that to 56, and subtract it to 56. I get between these values. And then 99.7 is 3 standard deviations, so multiply my standard deviation times 3, and then add it to 56, or subtract it to 56. So see how we can describe the distribution? Any confusion here? See how we can test to see if it'll fit with a normal model? Please note that the keyword here is approximate. It's not going to be a perfect normal model. Remember I had said previously, you'll never get a perfect normal model. But we can base things off of the model, which is what we're doing here. So let's look at another example. A wildlife biologist examines frogs for a genetic trait that he suspects may be linked to sensitivity to industrial toxins in the environment. Previous research had established that this trait is usually found in 1 of every 8 frogs. He examines 150 frogs. Determine the mean and standard deviation. Verify that he can use a normal model to approximate the distribution. So how do I find my mean again? NP. What is my N? 150 frogs. What is P? 1 over 8. Which means Q is what?
7 over 8.
Very good. 7 over 8. So NP is 150 times 1 over 8, which equals, I guess since we don't have a calculator, equals 18.75. And then my standard deviation, can you remember that formula?
The square root of n times p times q.
Very good. Square root of everything. Square root of your total times your probability of success and your probability of failure. So that is the square root of 150 times 1 over 8 times 7 over 8, which equals 4.05. So I have my standard deviation. I have my mean. Can I verify that he can use a normal model to approximate the distribution? So tell me, does it pass with success? Does he have more than or equal to 10?
Less than.
Well, let's see. The formula is NP is greater than or equal to 10. So take N times P and I get what? 18.75. Is that greater than or equal to 10?
Yes.
It is. Now what about the probability of failure? N times Q. So 150 times 7/8. What number does that give me? 131.25. And that, of course, is obviously greater than or equal to 10. So yes, this can be, I can use the normal model to approximate my distribution. And like the last problem, what would you do? How would I find my 68% with my mean? Yeah, add 1 standard deviation and subtract 1 standard deviation. How would I find the 95%?
Multiply standard deviation by 2.
Very good. 2 standard deviations. And then the 99.7% is 3 standard deviations. So we're bringing back the normal model. Let's see. Speaking of the normal model, something I want to bring up is, remember when we asked problems like this? Given a normal distribution of values for which the mean is 70 and the standard deviation is 4.5, find the probability that the value is between 65 and 80, find the probability that the value is less than 62, find the 90th percentile. Can I remember these problems? Remember we had to use this formula here, find our z-score. Find our z-score by taking that value, that x value, subtract it from the mean, divide by the standard deviation. Gave us this, Then we had to look at our z table. Remember all this? And the z table told me my percentage. I'm doing b here. Notice it says greater than or equal to. And our z table has less than or equal to. So I had to subtract this by 1 to get a probability of 13.35. Remember all that, the z tables? Well, you probably have noticed if you went to your calculator and did, I'll bring it up actually. So you probably have noticed in your calculator, if you went second distribution and looked on down here, this is where we find our binomial distribution and our geometric distribution. You would have passed up the first options, which was normal distribution. So yes, the calculator can actually predict using the normal curve, using that calculation. So example here, probability that the value is between 65 and 80. Normally we would find the z-score here, and subtract the two. But for the calculator, it actually has that set up to where you can find the upper and lower, plug in the mean and the standard deviation, and it gives you that probability. Now notice with B, what do we find with B using the z-table? This is using a perfect normal curve. I got 0.135. But with the calculator, using this here, I got 0.1332603. It's a little off. And the question is, why? This is perfect. This takes into account infinity. Your calculator cannot calculate infinity. So when you're trying to find the upper limit, you need to use 1 to the power of 99. That's the highest the calculator's limit can go. Now, are there values greater than this? There's a ton of values, an infinite number of values greater than this. That's why the calculator is going to be a little bit off as far as thousandths of a decimal, because it's missing those extra numbers. But it is a very nice probability. See how close we are? So the calculator can actually calculate a normal curve just like we have been doing with binomial and geometric. So here's how you would do C. Here's how you would do the percentile. This is a good way to check your work, or a good way, especially if you're given multiple choice questions on the test. You can do it this way. If you're writing a response like my math lab, hopefully it's not asking you to round to the tens of thousandths, because you may be a little bit off based on the calculator and the actual normal model. I'll demonstrate one just to show you how do we type in infinity in the calculator. So I'll do B. Again, normally we would type in our x, subtract it from the mean, divide by the standard deviation, get a value, look up that value in our z table, and that z value give us our probability. With the calculator, we would go to, we're looking for C here. So my upper and lower range, let's go here, oops. My lower range is, I want to find values that are greater than or equal to 75. So I want to have, my lower range is 75, and all values greater than, I'm going to use 1E99. So let me clearly show you how to do that. 1, now where in the world is E? Right here. Notice the double E. So second, comma, gives me my E. And put 99. That's the largest number your calculator can work with. And then give it your mean, 70, and your standard deviation, and paste. And there's my probability. My probability of that value being greater than or equal to 75. And if we were to use, as you see here, C, the probability that the value is less than 62, well, we're going to negative infinity. So you do that 1E99, but you would put a minus in front. That's how you would write in the calculator, negative infinity. So, normal model, we have the normal option to do it in our calculator. Just watch out because it's not going to be exact. It's missing a whole lot of numbers. Test 1 times 10 to the 99 power. But the big takeaway for today is verifying if we can use the normal model.